All right, so this is section 4.5. This section is going to be split into several videos. To be honest, I'm not really sure exactly how many videos. At least 4, but probably a couple more than that, and some of them will be fairly short. All right, so let's just talk about exponential equations, first of all, and this property of logarithms. This property of logarithms says if I have an x is equal to a y, some two statements are equal to each other. This says that I am allowed to take the log of both sides, and that can be any kind of log, any kind of base. So I'm allowed to take the log of both sides. A backwards version of looking at this exact same property is to say that if you have a log base A equaling a log base A, such as you have here in this case, log base A is equal to log base A, then I can go backwards to saying, oh, well then if my logs are equal, then whatever I'm taking the log of must also be equal. Now let's talk about solving exponential and logarithmic equations. I've already got this filled out, so you may want to go ahead and pause the video and fill out this box. But what I'm going to do is work through examples as I work through little tips here. So solving equations, you want to change your equation into one of the following forms. And that's basically going to be the first 3 forms. We'll also look at the 4th form as well, but the first 3 forms are going to be the ones that we're going to look at mostly here. So this first tip says that for the exponential equation, okay, so that's the first thing, is that I'm looking at an equation that is in exponential form. Another way of saying that is my unknown is in the power. So if my unknown is in the power, then what you want to do is you want to get your base and your power alone. And you're going to solve by getting bases alike. We did this back in section 4.2. Solve by getting bases alike, or by taking the log of both sides, and that is by using this property right up here. All right, so what I'm going to do is I'm going to forget about the rest of these tips for the moment, and we're going to go down and we're going to work examples 1 through 4. So example number 1, notice that my unknown is in the power. There's no way in the world that I can make my bases alike. Remember in section 4.2, we would make our bases alike. Well, I can't make an 8 base the same as a 21 base. So what we're going to do is instead is we're going to take the log of both sides. I happen to choose the natural log for this one just because I felt like using the natural log. I can use the power rule and I can get that power out to the front. And then I can divide on both sides by the natural log of 8. This is what's considered an exact answer. So sometimes you're going to be asked for an exact answer. Sometimes, as in this case, you're going to be asked for an approximation, because here it says that we should approximate to the nearest thousandth. So in this particular case, what you're going to do is plug that into the calculator, natural log of 21 divided by the natural log of 8, and you should get 1.464. Example number 2. In this particular case, notice that on both sides, my base and my power are standing alone. So what I'm going to start out by doing then is I'm going to log both sides. And this time I happen to choose the common log. I'll use the power rule. So both of my powers I'm going to swing out to the front. Please notice that my powers need to be in their own set of parentheses because it's the entire power that's being multiplied by the logarithm. At this point, I'm going to distribute. So my distribution, I'm going to take my log of 5, pass it to the 2x, pass it to the -3, take my log of 8, pass it to the x, pass it to the 1. Now at this moment, what I notice here is that in these 4 terms, 2 of my terms have an x in them, 2 of my terms, there is no x. So I'm going to get my x terms on the left and my non-x terms on the right. And then I can use my GCF on the left and I can factor out the GCF. Remember that the ultimate goal here was to solve. That's what we were asked to do, is to solve. So we want to get x alone. And so I'm going to divide on both sides by this whole entire quantity that's being multiplied by my x. So this is the original right-hand side, and let's divide by that quantity. Now, to be honest, this is a good exact answer. What I want to do from here is I want to show you that there are more answers that are considered exact, that are completely legal, that use some of the condensing properties that we used back in section 4.3. So I want to just walk you through how to condense this if you choose to do so. So on this first one, notice that I used my power rule, and that 3, I put it back into the power position. Same thing with the 2 down here on the bottom. After that, I used on top the, sorry about that. Up on top, I used the product rule, and on bottom, I used the quotient rule. 8 times 125 then is going to be, sorry, I uncovered the wrong thing, log of 1,000. And then on bottom, I have the log of 25 over 8, the fraction. Log of 1,000 is equal to 3. You can get that by typing it into the calculator, but think of it like this. You've got log base 10. 1,000 is 10 cubed. And so log base 10 of 10 is 1. If I use the power rule and pull that out front, that's going to be 3 times 1. So that's how I got the numerator there. All of these are considered exact answers, and all of them are good exact answers if you're asked for an exact form. But this one asked me for an approximation to the nearest thousandth, so we have 6.062. When you are solving an exponential equation, what's needed to remove the variable? You got to use the power property after you take the log on both sides. All right, we're going to do example 3a. Example 3b I'm going to come back to in a separate video. So once again, we're solving the equation and we're giving our solutions to the nearest thousandth. So I cannot make a base e and a base 50 the same, so I'm going to log both sides. And the reason I chose the natural log is because it can undo the exponential e. So let me stop right here for just a moment. If there's any tens in my example, I'm going to use the common log. If there's any e's in my equation, I'm going to use the natural log. If I have no tens or e's, eeny, meeny, miny, mo, pick whatever you want to pick. All right, so with that said then, the natural log of e raised to a power is just going to be that absolute value of x. Where did you get that from? Well, we had a property back in, it's the very last theorem in section 4.3. So if you go back to section 4.3 and look at the very last theorem, you'll see it there. Since my bases are alike, the only thing that's going to be left over is that power. What does the absolute value mean? Well, it just means that I can equal either a positive or a negative natural log of 50. And it did ask me for solutions to the nearest thousandth. And so we'll plug that into the calculator and you'll get a positive or negative 3.912. Skip part B, we'll come back to that. Let's go to example 4, which deals with solving an exponential equation that looks like a quadratic. Okay, so for the moment, let's pretend that e raised to the x is actually the same thing as an a. So I'm just taking all of my e to the x's and replacing them with an a. And so I have a squared minus 6a plus 5 is equal to 0. Well, we know how to solve this. We've been solving this since the beginning of the semester. I like to use factoring on this. So this will be a minus 5 quantity times the quantity a minus 1 is equal to 0. So that my two solutions are either a equals 5 or a equals 1. But I didn't have an a to begin with. I had an e raised to the x. So let's take it back. And everywhere I see an a here, I'm going to replace it back with my e to the x power. So in my factored form, I have e to the x minus 5 quantity times the quantity e to the x minus 1 is equal to 0. By the way, if you FOIL that out, you are going to get the same as what the original equation is. And so now I can say, well, e to the x is equal to 5 or e to the x is equal to 1. And remember that in that gray box, one of the things we wanted to do first was get the base and the power alone. So that's what's happened here. I've finally gotten my base and my power alone. And now I'm going to log both sides. Well, since I'm using e's, I'm going to take the natural log of both sides. And we understand that the natural log of e raised to the x is just going to be an x. And over on the other side, same thing. And any log of 1 is equal to 0. Once again, this is a property back in section 4.3. So you'll want to go back there and take a look at the properties. Now, take a look. On this one, I was asked for exact values. So I'm not going to go and plug these into the calculator. All right, so this is the end of the first video. So stay tuned for the next video.